Hello, everyone, and welcome. We're going to get to it as quickly as we can. So, we're going to finish up as this first part. We're going to finish up chapter 8 and then start getting into chapter 9 and see if we can get into the completion of that for this week so that we can kind of get back on track because there's so much to cover overall. So, here's where we're at. We're thinking about what engineers need to consider in terms of fracture design. So we talked about stresses and cracking, and this process is very straightforward. It requires it's something that you'll use a lot more in some other areas for design, but it's a ratio. The stress concentration factor is a ratio of the max in a especially a reduced area relative to an original area of the stress. So the max stress divided by the nominal stress across the whole part is that level. So the degree to which this has changed these dimensions, that increasing width to height ratio, meaning the more aggressive the narrowing of your sample is, or the more aggressive the size change, the higher up the stress concentration factor, meaning the stress that won't break the part here at the top could break the part here at the base because of that significant difference in cross-sectional area, is really what it means. This has to do with crack propagation, and that means that cracks tend to have a sharp tip rather than a blunt tip if it's ductile rather than a brittle fracture. A brittle fracture is going to be a lot less plastic in its behavior, and therefore it's going to be much faster moving through the material. The brittle crack is going to move at a much faster rate typically, so they fail. Another part of the reason why they fail explosively in experiments is that exactly. So the deformed region in the ductile sense becomes less and less and less sharp. It's that deformed region at the edge of the ductile crack becomes sort of blunted because the material is stretching at that point rather than simply breaking immediately. So there is an energy balance that's happening, and there's a difference between the elastic strain energy and not. So the energy that's stored in the material as it's elastically deformed is released when the crack propagates. So that energy is stored and released, stored and released, stored and released in a rapid cycle. It's faster in the case of the brittle relative to the ductile sample. But it has to create a new surface, and that process, again, thinking back to the molecular level, you're making and breaking bonds that requires the input of energy. So a crack doesn't just propagate on its own. There has to be some amount of energy, and that's going to be the way that these propagate in practice. So the criterion for crack propagation is that the crack propagates with a tip stress, so sigma m, and that is greater than the critical stress sigma c, the critical stress being defined by 2 times the modulus of elasticity, i.e. Young's modulus, times gamma s, gamma sub s, the specific surface energy. So different for all different sorts of materials, depending on its composition, depending on how it's doped or what materials are substituted, like we've seen in other areas, especially with all the substitutions that happen in ceramics. That gamma can change significantly, divided by pi times 1/2 length of the internal crack, meaning cutting the crack in half to evaluate the energy so that you're not double counting the amount of energy. You're only looking at half of the picture because there's a mirror effect that happens there. So the square root of that quantity is the critical stress, and where the crack tip stress exceeds the critical stress, the crack will propagate. That's a thing that rationally makes sense, so we shouldn't be very surprised by it. Broadly speaking, for the ductile materials, you replace gamma S with a combination of gamma S and gamma P, where P is the plastic deformation. So it's has to do with the specific surface energy, but also the plastic deformation energy. So how much energy it's being absorbed, and that being in the numerator is why the materials that have a plastic deformation mechanism mathematically, that's how we represent that they take more energy to continue making and breaking those bonds, because they stretch those bonds farther, typically during that deformation process. So range wise, metals on the far left are significantly greater in terms of their fracture toughness. That shouldn't be hugely surprising to us. It's very easy to break ceramics. If you drop a cup on the or especially a mug or something like that on any kind of hard surface, you get a shattering of the material. So a lot of some of the aluminum oxides and some of these things are up here to the right side with composites. The actual fracture toughness of those carbons are very, very high. Some of the glasses and diamonds and things are very, very high. Things that are very small fracture toughness are things like polyester and concrete. Those sorts of things. A lot of the polymers have a very low fracture toughness, so they aren't immensely strong materials. Glass by itself is, again, not very strong against fractures. So it's very strong in compressive loads, not very strong in tensile loads, and very poor in terms of its fracture toughness and what that is. So this is a useful chart. There's a lot that we could talk about here, but in the interest of time and getting caught up, we're going to continue moving. So the design against the crack growth and some of the things that happen there, in order to think through how do we keep that from being a major malfunction in our material. And you might be thinking, well, why is that going to be something that's important? Think especially about materials that are deployed for a specific role that someone's life depends on. So something like a vessel at sea is a simple example to think about. A vessel in space is even more important, because any kind of stresses and crack propagation is exceedingly detrimental in space. It's a huge problem if you have a cracked material in space. So you want to avoid that at all costs. But even at sea, a cracked vessel is a huge, tremendous problem. And there have been a lot of issues with ships having hull fractures and things throughout sort of all of maritime history. So there's a lot of things that we've learned over the course of these years that we now have a better understanding of. So the idea is, so long as that critical stress is not exceeded, there's a couple ways to think about this. So the max flaw size is one concept. So the size dictates the design stress. So your stress design is this KC, this critical value for stressed cracks, divided by this modulus times the square root of sigma A max being the, just like we saw here, 1/2 length of the crack. Same here, where we change the formula slightly for the concept, where we say this dictates the max flaw size, rather than the max flaw size dictates the design stress. We can say it the other way around and say, well, if the design stress dictates the maximum flaw size. Little bit different mathematical representation. It's an inversion of the other scenario here. So we have an inversion to describe what the max flaw size is. So that half crack length. So two different ways. It's the same equation, just presented from two different viewpoints. No fracture is below the curve, fracture is above the curve. So the important thing to understand out of all of this is where does the fracture occur? Well, it occurs above this threshold. So we want to keep it underneath this threshold, regardless of which scenario we're evaluating, but it allows us to understand, based on this fundamental equation, it allows us to understand how we can design the material. So we can change materials, we can't really change the coefficient of a material, but we can change the material, therefore changing the coefficient. So for something like an aircraft wing, again, something that lives are relying on, where cracks are exceedingly bad and could lead to imminent death, we want to pay very careful attention. So the material has a Kc of 26 megapascals meters, square root of meters. It's a kind of a confusing unit, but it's again a constant to help us relate materials to another material. So don't get hung up on what does that actually mean. Focus on the design aspect of this is a coefficient that allows us to categorize materials differently based on their failure behavior for crack propagation. So it's a different way of hiding our ignorance in a constant that allows us to compare different things and say, oh, that one's better because the number fits what our design requires. So if design A says that we can't have a flaw beyond 9 millimeters and the failure stress is 112 megapascals, design B says use the same material, the largest flaw is 4 millimeters, what is the failure stress? So you forward calculate with the one instance, and you say this sigma C is equivalent to, and we plug in our constants. We end up at a place where we determine, based on the way that this works, 112 megapascals and 9 millimeters is the largest flaw size, is equivalent to the critical stress times the square root for design case B. By equating these two and balancing the two equations, we can determine what that other material would need to be. And so 168 megapascals would need to be the critical stress of the other material. The way that we understand this for a material is we measure it. We don't guess, we measure it. And this is also a way that we validate materials that have been developed. So you'll be doing one of these kinds of tests called a Sharpie impact test. The Sharpie, spelled different from the kind you write with, just something of note for your lab instructors so that you don't get points knocked off. The Sharpie is the sample type named for, I believe, the person that came up or is credited with the test to begin with. So it's an impact loading case. You have a specimen, you have a hammer, you have a starting position, you have an ending position. The difference between the starting position for the pointer and the ending position gives us the ratio, because of the differences in height of the material in the hammer. The differences in the height tell us something about the differences in potential energy at the beginning and the end of the sample impact. So the sample breaks in the process unless it's beyond the range that that particular Sharpie tester is rated for, which can happen. That was one of the first things done with the samples there at GCU, is some much too large samples were put into place and dented and bent some things that shouldn't have been dented or bent. So it happens. The impact loading is then proportional to the difference between those. Now, our particular style Sharpie tester doesn't give you that. It gives you an energy reading after the fact, but it at least allows us to better quantify and compare the results together. So it'll help to kind of see this and experience this, but that impact energy is a thing to pay careful attention to. So there is a ductile to brittle transition temperature, and a temperature is another variable that you're going to play around with in that particular lab. Below that transition temperature, things behave more brittle. Above that, things behave more ductile. Irons and things of that nature, a lot of the steel materials have to be fairly low temperature, and the way that we get there in that particular lab is by way of some dry ice to be able to cool it sufficiently to get it closer to that more brittle state. FCC metals are much, much, much higher in the total impact energy. So these are the copper, the nickel, things of that nature. BCC metals and polymers tend to be in that range described by the red curve. The high strength materials with a very high stiffness, so modulus of elasticity divided by 150, if it's greater than that value, it's going to be in that high strength region. So it's going to behave much differently than some of these other kinds of materials. So they are going to behave more brittle. So they're going to snap at a much lower impact energy typically. The higher impact energy is the stuff that has more physical dimensions to be able to absorb all of that energy into. So they bend and move a lot before they actually fail. And that's why things like copper and nickel, so metals that are softer, are behaving more brittle-like, which is why that's to the left side. So the brittle materials are below. The more ductile behavior, and polymers especially, are very, very high in terms of impact energy because they absorb energy as they stretch bonds like a rubber band. So if you hit a rubber band with a hammer, it behaves a lot differently than if you hit a very high strength alloy with a hammer, where it might not move significantly, or it's once you finally reach the impact energy, it's going to be shattered. So an example of this, many have heard the stories about this. The Titanic is an example of this. So a series of fractures that happened that created problems. The Liberty ships in World War II was another example, and this is one of the ones that I thought of first. The steels that were used for these ships had a brittle to they had a ductile to brittle transition temperature below room temperature, making them very fragile. So the example of what they did in order to fix some of the things for the Liberty ships was to create these long bars that would go on the side of the ships to be reinforcements using a different material, a different grade of steel. So important lessons were learned, even though lives were lost. So it's important to understand how it all works and why we need to understand these lessons. So this was something that was not that long ago, and it was thought that if you make them out of steel, as long as it was steel kind of steel, it probably didn't matter. It turns out it actually really does. So there's another concept that happens in these metals, and that can be described as fatigue. So this is something that happens with cyclic stresses. So you have a measurement, you have some sort of load, you have a transducer, we've seen a lot of examples of how some of these kinds of measurements can be done, at least with strain gauges and all sorts of things. You develop load cells using strain gauges, and that allows you to connect a specimen between these bearing housings in order to test them. You have some sort of coupling and a motor actuator and some sort of counter to keep track. The stresses that vary with time. This is part of the reason why the practical testing of things like IKEA furniture have the seat sitting simulator and some of these other kinds of things that are cyclic stress testing. They are testing for fatigue. How many sits does that particular design have before there is a failure point? At some point there will be a failure, but their counts are usually extremely high. So it's a stress that varies with time between a maximum and minimum value, and it is often periodic or can be described by some sort of periodicity. And the idea is that fatigue can cause part failure even though the max stress experienced is significantly below the yield stress for a sample. And 90% of the mechanical engineering failures are because of these kinds of loads that happen. So countless examples of bridges failing and all sorts of things, physical infrastructure failures of that kind. So this is all part of the reason why it's important to understand the way that these materials act and behave and interact with each other, in order to understand what happens and how some of these work in their end application. So it's important to know what the material has to do, what the limitations are, what the required safety factor for that sort of application would look like, and what the fatigue limits would look like given the sum total of the things that you've learned over the course of this semester and some of the lessons that we're getting into in the next few chapters. So there's a fatigue limit, and there's a that's referred to as SFAT here. So there's a safety range, and then there's an unsafe range. So above that curve, there's a number of cycles to failure that will happen. So there's something like the case for steel, something like 10 to the 6th cycles above this range, above this limit, gets you into an unsafe territory. So some materials don't really have a fatigue limit exactly. So aluminum is a lot more flexible typically, and so it won't have sort of a threshold above which fatigue happens. So it tends to have a slowly degrading performance over the course of time. This becomes important especially for things like keyways in shafts that are transferring torque from something to something else. So lots and lots and lots and lots of examples of failures in rotating shafts. They can be axles on cars. They can be all sorts of different things. They can be rotational centers for all sorts of things. There's like mining operations, drilling operations, lots and lots of different kinds of equipment have to have variations of shafts with keyways and things. And you get a crack and fatigue that happens with these, and the growth can be described by this concept of the increase in the crack length per loading cycle can be described as effectively the change in stress times the square root of that, again, that half length of the crack. So In the case of something like this rotating shaft, there was a keyway, and that keyway was the origin of the failure. So that keyway was keeping the shaft from rotating inside of whatever housing it was in. And that failed right at the sharp corner of the origin. So the crack grows faster as that change in stress increases. The crack gets longer, the loading frequency increases, especially for something that has to rock back and forth or oscillate. That can be very, very key. So it gives you the idea of the direction of rotation, and you can see that in the curved lines. So the direction of the rotation is in this general direction. So it's a counterclockwise rotational direction, and then the final rupture is here at the base. This becomes important because you can change the surface stresses. So this is what you guys saw some of the examples of in glass, especially. They change some of the surface stresses by changing composition and all sorts of things in order to suppress, in this case, in the case of metals, you're looking to suppress the surface cracks from growing. So prevent them from growing any farther. So the stress amplitude, as that goes higher and as the number of cycles to failure goes higher, you can, the best thing that you can do is you can change what material you're using based on what kind of cyclic stresses you're going to be applying, so that you get toward near zero or compressive stress. So shot peening is a very common example. So you'll see shot peened chains, for instance, and chain links are much greater in strength than a chain material that hasn't been shot peened, because they literally shoot shot at it in order to make impressions in the surface that compress those grains together. That compression in the surface makes the material much harder, and therefore you can also do this chemically with some exchange, so carbon rich gas and things of that nature, and you can change the surface concentrations and add compressive stress. We've seen that in other examples and other things, other areas that we've been using as references as we've been going along. You can then improve your design by reducing the stress concentrators by adding radii where sharp corners are, so that you don't have a single step from a lower stress to an immediate higher stress, creating a designed failure point right at the transition. So the reason we do fillets and things in the drawing stages is we know that sharp corners tend to concentrate stress and create points where our stuff is going to want to fail. So we want to make it harder for it to fail by choosing better materials, by choosing better grades of materials, and by eliminating, wherever reasonably possible, sharp transitions from one geometry to another. The smoother we can make that transition, the longer the longevity of our sample or part is going to be, especially under cyclic loading. And that's very, very important for longevity. Creep is another phenomena. No, not talking about a lot of other definitions that you could come up with for this. Creep is the idea of a material moving over the course of time because of stress. A simple way to think about this is the float plate glass in like stained glass windows and things from very old architecture. The glass has a very, very, very slow creep, so that you can measurably see the difference between the top of the glass in terms of thickness and the bottom of the glass. So the bottom of the glass is where a lot of the material will collect as it continues to creep over the course of time. So over a very long time, you have more and more and more strain built up in the material. You can reach a point where, depending on what it is, you can have rupture. So you have an instantaneous deformation, and then you have creep over the course of time. Then you have secondary, which runs at a much, much slower pace. Then you have tertiary that accelerates as it becomes more and more and more strain built up in the system. So there's a creep rate that decreases with time. There's a steady state phase, and then there's an increased or acceleration of creep of the material. You can think of plastics that do this. If you were to try and stand on if you were to take a whole bunch of like paper towel tubes or something and stack them all side by side, put some sort of a board on top and step on top of it, you could gather enough that it would hold your weight for a minute or two. But as you continue to apply that load, you're going to have the material slowly begin to creep until you start to get some reaching this tertiary phase. You have an acceleration, and then ultimately what would be the rupture, where all of a sudden a tube wall collapses because of the stress at an angle or whatever is happening there. All of a sudden that collapses, and then the whole board collapses because you get an acceleration of this rupture. So that's exactly what creep does. But it can be over very long times, including literally centuries. So I think if we were to still have some of the original glass that was used in some of the structures from the Roman era, they would have been nearing that tertiary region by this point in time. So there's a temperature dependence, and at elevated temperatures, think more kinetic energy for those molecules, creep becomes something that happens at a much faster rate. So you have a primary region, you have the secondary region that's steady state, and then you have the tertiary region. So the higher the temperature, especially at temperatures above 0.4 times the melting temperature, so half of the melting temperature, you would expect a material to creep very aggressively. The higher that ratio goes with increasing temperature as it reaches the melting temp, creep transitions into flow at the melting temperature because it transitions from a solid to a liquid at that point. And so it continues to increase and increase and increase until it just becomes a point where at that melting temperature, it's completely, strain is effectively infinite because there is no more change in length with respect to the original length when it does a phase change. There can be secondary creep in a material. So a strain rate is constant for a given temperature and stress, and strain hardening can be balanced by recovery in that circumstance. So you have a strain rate, and this is one of those things that's crazy to think about, but it's a reality. The reason that a scalpel, when it's cutting tissue, for instance, is the reason it is able to cut tissue so effectively is because not that it is just 10 million times more sharp than any other metal. That has actually nothing to do with it. The specific geometry of the blade and the kind of compression and various things that are happening to the tissue at that point creates such a high strain rate. It is an optimized strain rate, this epsilon s dot. That high strain rate is actually what causes the tissue to effectively unzip, because all of those proteins and connecting, joining macromolecules, part of the cytoskeleton, and all of those things, they cannot handle the rate of energy transfer because of the strain rate created by that blade. So the shape, the geometry, the pressure, all of those factors, the overall width of the contact patch with respect to the sample, that creates such a high strain rate that it effectively unzips the tissue. So there really isn't actual cutting of the blade, severing bonds and using a lot of energy. It's the strain rate. It's an extremely high strain rate that creates that problem. So that's the same kind of thing that can happen under the wrong circumstances to a material that you're using to design something. So you have some sort of material constant, you have a stress exponent that's dependent on the specific material, whether it's a steel, a titanium, some kind of alloy, that's going to vary widely. You have the applied stress, and you have the exponential factor that has to do with the activation energy for creep. So that's, again, material dependent, divided by RT, the gas constant, times temperature. So that has to do with the kinetic energy and how much energy is going to creep. That ratio is an exponential factor, but that reduces, it's a negative. So it's a reducing exponential, because the more activation energy needed, the less of a temperature dependent effect you're going to have on that strain rate. So that should make sense rationally. When we plot this, we get something like this, where you have a steady state creep rate, and at different temperatures, the stress becomes lower to achieve that same stress steady state creep rate. And that makes sense. So as that kinetic energy in the system builds up at the higher temperature, the lower the stress required to create that strain rate, in order to get that propagation of materials failure. So the creep failure can also look like this along grain boundaries, where you apply the stress and you slowly get cavity formation, meaning separation at the grain boundaries. So you wouldn't expect the grains themselves to be coming apart, but the grains start separating away from each other under that stress, because that's where the bonds are slowly breaking over time. Those are the lower energy bonds to break because they're often at odd angles with each other. So the contact is not as good. It's easier to stretch those bonds. So those are the ones that fail, creating this process. So understanding how to predict the creep and rupture lifetime gives some sense of what's actually going on here. So the estimated rupture time for something like an S590 iron, given 800 C as our temperature and given the stress of 20,000 psi, is this is an interesting length of time. It's in Kelvin hours, the way that it's presented here. So it's a factor including temperature and time. So the longer that stress is applied at that given temperature, the lower the overall stress is to create rupture. So the material weakens over the course of time. So this is part of the reason why they would have to do work and replace parts on especially things like boilers, cast iron boilers and things. This is why these kinds of things happen. So these materials, we saw examples of boiler ruptures in some of the accident report things that we saw. Same kind of thing that's happening there. That prolonged high temperature use at a given stress over the course of time, especially with the thinning of material and all of these things. All of these parameters add up to the failure because of creep and ultimately rupture of the material, along with corrosion and all these other factors. So there's a lot to consider when we're putting a material into an end use application. So the time to rupture can be approximated as The temperature times 20 times the log, this is the log of time to failure, is a function of the applied stress. So for their example here, at 1073 Kelvin, so 800 plus the 273 to convert it to Kelvin, so 1073 Kelvin plus 20 times the log of the temperature for rupture is equal to 24 times 10 to the third, because that's our units for the function of the applied stress there. That's Kelvin hours, is approximately 233 hours. So given what this iron's going to be subjected to, 233 hours is your expected time to failure. So a lot of things in practice are not as strong as the theory would just blindly predict, and that becomes very important for a lot of reasons. So the flaws act as these stress concentrators to create a failure because the stress is much higher at that concentrated point than what a theoretical value would say. That sharp corner introduction produces large stress concentrators and creates the condition for premature failures, especially in terms of shear. Not always so much in tension, but almost always in shear. They become very, very vulnerable in shear for stress concentrators. The failure also depends on the temperature and the stress that's applied. So for simple fractures, there's non-cyclic stresses and temperatures below 0.4 times the melting temperature, or 40% of the melting temperature. The failure stresses decrease with the increased maximum flaw size, decreased temperature, and increased rate of loading. So if that load is applied and unapplied faster, then there's less of an issue with the cyclic loading. For fatigue, the cycles fail to decrease as that change in stress increases, and for creep at temperatures above 0.4 times the melting temp, or above 40% of the melting temperature, the time to rupture increases as the stress or temperature increases. So there's a lot of design considerations that come out of these, but that at least gives a reasonable starting point for a lot of what's going to happen, or a lot of what will ultimately come as a result of design choices for materials. So this is where we'll finish up on chapter 8, and we'll start jumping into chapter 9 so that we can get through as much of that this week as we can. All right, chapter 9. This becomes critically important for a lot of reasons. Some of the things that we want to keep in mind are that when we combine a couple different elements, we have some sort of equilibrium state. So this is getting into some of what to expect in terms of how the composition of atoms changes the behaviors of the material. What does that look like for grain structures, and trying to tie a bunch of these seemingly almost unrelated concepts together all under one total phase. So this is something that becomes critically important, especially for things like copper and nickel. We're going to spend a lot of time in the iron phase diagram. We want to understand what changes as a function of temperature, how many phases form, what is the composition of each phase, and what's the amount of each phase that's present. So in the case here, where we have copper and nickel together, phase A and phase B are very different in terms of their ratios, their composition, as well as their actual crystalline structure and how all of that works. So there is a solubility limit. That means for a solution, it's a solid, liquid, or gas solution, single phase. So there's a max amount of one thing that can be dissolved in another thing. or a mixture of other things. Mixture is more than one phase. So those are distinct terms and things that you should remember from chemistry. The solubility limit is how much concentration can something have while there's only a single phase. So in the case of developing the well-famed sports drink Gatorade for the Florida Gators, in case you didn't know why that was named what it is, they wanted to get more and more and more electrolytes into the players during the course of the games, but they reached what was called a solubility limit. So they couldn't add any more salt and sugar and anything else into the water, and they couldn't get past the solubility limit. So what did they do? They added a third thing in there, basically a solubility aid. So in that case, it was something sort of related to the polymers that keep coolant in your engine from freezing, and they added this plastic, this polymer, into the liquid to help force more stuff into that liquid, and decided to give it to the players. And long story short, now we have diabetes in this country all over the place, and obesity and all sorts of things. So solubility limit is a barrier or a boundary above which you won't be able to maintain the same single phase, and you can't really have a true solution. The reason something like Gatorade was so clever is because it cheated and changed the base of the liquid in order to continue being a liquid. So the solubility limit for sugar at water at 20 degrees C is 65%. That's a lot. That's effectively called syrup. And if you go above 65 weight percent, you have sugar plus syrup. So that's your limit for syrup. So all syrups are some combination of sugar and water. So that's part of the reason why that is interesting, because it's added to so many of our drinks, especially. So the components and phases in a metal are similar in concept to that, except that they are in the alloys especially. You can have things like aluminum and copper, physically and chemically distinct material regions that have alpha and beta. So the alpha is the darker phase, the beta is the lighter phase, and this aluminum copper alloy is just one example that we'll look at from this. So one thing that you can do is you can increase the temperature. So as you increase the temperature, more kinetic energy available for all of the things, and you go up to the boiling point, for instance, or near the boiling point, and you transition out of the liquid region at that point. But you can transition based on temperature, or you can transition based on concentration. So you can above, in that case, 70 C is your liquid transition. Then you can add more and transition back across that phase line at a given temperature. So for solid solubilities, there's a way that we can think of this a little bit simply, and there's a relationship with electronegativity and the radius of the materials. So what does all of that look like? Both have the same crystal structure and have similar electronegativities and atomic radii. So these are referred to as Hume-Rothery rules, suggesting a high mutual solubility. Nickel and copper are soluble in one another for all of these proportions. They are similar in electronegativity. They are very similar in radius. They are similar in crystal structure, so they are going to be very easy to dissolve one in another. You're not going to take a ton of energy to force copper into nickel or nickel into copper. They're going to coexist rather politely together in alloys of all different concentrations because of that. Some things don't behave that well, and we need much more clear phase diagrams. And so these are fundamentally something that we need to understand. You may come across these, if you haven't already, in your other classes. One of those being the thermo class. So you'll see probably some example of phase diagrams there as well, because we need to understand phase transitions of things and what the phase envelopes look like. So here we have an example of the liquidus line and the solidus line. So below these temperatures at these given ratios, we have a solid. In the middle, we have a liquid plus solid. And above this liquid envelope, we have all liquid. That becomes very important, especially for casting of materials, and we'll come back to some of those concepts. But we start by understanding some fundamentals about the phase diagram. So this is a weight percent nickel. So from 0 weight percent nickel to 100 weight percent nickel, we see two different melting points. So this is pure copper, this is pure nickel at this edge. Everything in between is a different ratio. So as we add more and more and more nickel, the melting point goes up. And if we transition to something in the middle here, at a 50-50 ratio, we could go all the way up to almost 1250 C before we start getting some liquid. But we have to continue heating all the way up to 1300 C at that composition to reach the that liquid phase. So even though it starts to melt at 1250, we have to reach a full 1300 at that ratio. Same thing over here, about 70%. We hit that just a little over 1300, probably 1320 degrees. And then as we continue heating, we have a mixture of liquid and solid. And then about here, so somewhere across around 1380 or so, we reach the liquid envelope. So we can understand some different things that are going on. We have our solid, our alpha, we have our solid plus liquid, alpha plus L, and we have liquid. So this is for a simple example for the copper nickel system. So it's binary, it has two components, and it is what's called isomorphous, meaning that the complete solubility of one component in another component is possible. So alpha extends from 0 to 100 weight percent nickel. Again, most things don't have the exact same crystalline structure, very similar atomic radii, and most things don't behave as nicely as these two do. So this is the very simplest example of what this can actually look like. And there's a lot of reasons why it can become so easy to miss some of the details. You'll see here very shortly as we start getting into some more complicated materials, how these phase diagrams change, and we have lots of different regions because of the way that they behave. So things that we want to know as we're looking at the phase diagram, we know a temperature and concentration for that given set of coordinates on our phase diagram. We know which phases are present and how they're behaving. So at 1100 C, we know for 60 weight percent, we're in the alpha phase. At 1250 C, we are, and 35 weight percent nickel, we are a combination of alpha and liquid. So if we know the temperature and the concentration, then we can determine the composition of each phase. So we're going to look at a sort of thin slice here. so that we can look. And there's a tie line method that we're going to use that a lot of students can get super duper confused on. So I'll try and make sure this is pretty clear. So let me back this up just a second. So we're looking at just a smaller section closer up in this phase diagram. So at 35% copper, or 35% nickel in copper, rather, we start with step 1, which is all the way up to A. So the temperature at A is 1320 C. That means there's only liquid present at that point. If we cool it to 1190 C, that same material exactly, we know we're going to have only alpha, so it's going to be all solid. If we bring it back up to temperature 1250 C, we're going to be right in that middle region where we're going to have both alpha and liquid present, because we're inside that phase change envelope. So this tie line tells us a lot about the composition. When we are at temperature B, what that means is we look all the way to the left side, and that line intersection point gives us our 32 weight percent nickel in our liquid side. And on the other side, the concentration in the solid is 43% nickel. So even though our sample only has 35% nickel to begin with, based on the temperature and what composition is liquid versus solid, these tie lines tell us about the composition of each phase and why it is different. So it's okay to go back and sort of rewatch this several times to make sure that you're actually understanding. The reason why we need to know these tie lines is in that phase envelope, anytime we're inside a phase envelope, regardless of what the phase envelope is representing, it could be alpha and beta, it could be beta and gamma, it could be 37 other things, it could be trinary, but I don't think we get into any of those in these chapters. Trinary phase diagrams are nightmarish to interpret, but still important. So these tie lines help us to understand. On the liquid side, we drop the line straight down to 32 weight percent nickel. On the solid line, we drop it down to 43% nickel. So even though it's transitioning, if we continue heating that same material, we will get to a liquid that is uniform again once we hit that liquid line. So these give us some important key perspectives. So the weight fraction of liquid at point A is 1, meaning 100% liquid. The weight fraction of alpha at point D is 1, but we have to calculate for point B what these are. So S over R plus S, this is R and this is S. For liquid, it's for the thing on the left side, it is the right side divided by the sum. For the thing on the right, the solid, it is the left divided by the sum. So each one, we look at the opposite side. That's just the rule of thumb. So really pay attention to this, because you're going to come back to this when you have to do this on an exam, because you will have to do this on an exam. So we get this ratio 45 or 43 minus 35 is the distance or the length of that tie line. The length of that tie line divided by the whole thing, which is the same as 42 minus 32, so the whole length. The ratio of that length divided by the whole length gives us 73% liquid and 27% solid. So we can determine based on these tie lines what the amount of, or the weight fraction of liquid versus solid is. And because there is no conservation of volume, but there is conservation of mass, we want to know what the mass ratios are, these weight fractions are, because mass is conserved regardless of phase. Volume is not. That's a very, very key, important aspect of all of this that you guys need to be able to take away. There's a lot more to that, but we need to at least cover some of those key parameters here. And this is another one that is critical to understand, the lever rule. So the tie lines connect these phases in equilibrium with each other, and they sometimes are called an isotherm. These isotherms are an important aspect of, for a given temperature, what our ratios are. So the weight fractions differ greatly, but they balance each other out. So you can think of them as a teeter-totter, and we need to understand how that works. So M alpha times S is equal to M liquid times R. And that's why we have the balance. That's how you get to the S over R plus S and the R over R plus S for these respectively. That's why it's looking at the opposite side, because it needs to understand with respect to the balance of the equation that's presented here. So the teeter-totter has to be in balance in order for any of this to make sense, because otherwise you would have a missing mass problem, and you'd have a lot of issues there. So that's the tie line is the thing that connects these together, and the lever rule is what creates our shorthand equation. So that S over R plus S, that becomes critical to remember in the actual examples that we're going to look into. So then as the phase diagram, we go through cooling. Again, if we start at A at 1300, 35 weight percent nickel, as we cool to the very first edge of that envelope, we get a very, 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 very small tie line to the left and a very large tie line to the right. So we start at 35 and 46. We draw our line. So we start at 35% nickel in the liquid, and we start at 46% nickel in the solid, just as we hit that temperature, as we hit that phase boundary. As we drop lower, that composition changes, and those solid grains with the higher concentration of nickel begin to grow, and more of the copper is growing. So a lot more of the copper is being absorbed. So the ratio of nickel in the solid phase becomes lower as more of the copper condenses into those grains. So the copper reduces from 35 to 32 in the liquid. The nickel reduces from 46 to 43% in the solid. As we reach the lower threshold of that phase envelope, that biphasic envelope, the copper composition in the liquid drops to 24, or the nickel concentration drops, rather, since we're looking at just the nickel concentration. I need to be really clear here. That nickel concentration drops to 24 and in the liquid, and drops to 36 in the solid, until we reach that bottom phase where we're back to 35 weight percent nickel. So even though the starting and ending points still have 35% nickel, the period in between where you have two phases, you have differing ratios in those grains. So it's really, really important to understand the difference between chord and equilibrium structures, and this is why. So the concentration of alpha changes as we solidify because of how those different materials are behaving, and it's relative to the actual thermal capacity, the heat capacity and things of those individual atoms as they differ. That's the main reason why you have a phase envelope like you do there with biphasic region. So slow rate of cooling, the equilibrium structure results in 35 weight percent. The fast rate of cooling creates at a differing rate. So you have a first alpha to solidify at 46 weight percent and a last alpha to solidify at less than 35 weight percent because there's not an equilibrium between them. So the case of the left side here is slowly cooling, like pull it out of the furnace and let it cool in air, kind of cooling. This is rapid cooling, which creates layers of decreasing concentration. So it is possible to get higher concentration and lower concentrations and have unusual tiered grains like that. It is possible. So the solid solution strengthening means you can add or take away the material, but that tensile strength as you add, so pure copper is off to the left side here, a little over 200 megapascals. For pure nickel, it's a little around like 340 or so megapascals. When you put the two together in the right ratio, you can exceed about 420 megapascals, somewhere around 60% nickel. You get a very, very strong alloy. So it behaves stronger than either of the two pure components. And that's part of the reason why we alloy things in the first place. Your ductility also changes. So for pure copper on the left, pure nickel on the right, ductility decreases significantly at that 60%. So it's the inverse, effectively, of the tensile strength. We've seen that in many cases, and that's a normal inverse relationship, because as things become more ductile, they become less strong. As things become more strong in tensile strength, they become less ductile. So they become more brittle-like. So we expect to see that sort of inverted relationship. Now we get into binary eutectic systems. And this is where we get into just so much more than what we've seen so far. So this looks a little bit scary, but we're going to break it down. This is a simpler system than something like steel and some more complicated materials. The iron phase diagram we'll learn about later. This is one that has a specialty composition that has a minimum melting temperature. So a binary system meaning two components. Eutectic meaning it has a composition at which there's a minimized melting temperature to reach the liquid phase. So anytime you see this, you're going to have a eutectic or a eutectoid point we'll get to later. For now, we're going to say this is the eutectic point. So you've heard of maybe something like in the automotive world, you've heard of something like hyper eutectic alloys or something. So just above or just below the eutectic point in terms of concentration or ratio of, in this case, it's weight percent of silver. So above or below 71.9%. So if you had 70%, that would be a hypo eutectoid, if you had just a little more than 73% or something, you would have a hypereutectic alloy, meaning they could melt it and cast it at a lower temperature. So the difference between 800 C and 1100 C is a lot in terms of energy. Therefore, processing expense in order to work the material. So there's an appeal to being able to use something at a eutectic point. The downside is it is a weaker material than something of, for instance, a different percentage. So whether the alpha grains or beta grains are stronger depends on the specific material and a lot of other factors. So the melting temp isn't necessarily an indication of tensile strength or anything of that nature. It simply gives an idea of what the phases are based on temperature. So this is right at 779 C, where that 71.9% happens. So there are three single phase regions, alpha, liquid, beta, and one multiphasic region. There's three of those as well. So you have liquid and alpha, you have liquid and beta, or you have alpha and beta, and you have liquid and beta. So there's no alpha above that eutectic point. This is where that phase diagram and the tie lines become really, really important to understand, because if you draw a line across, you don't get into beta unless you're above this eutectic point, or you get beta if you are below the eutectic temperature of 779, the eutectic melting temperature, 779 C. So in alpha, it's mostly copper. There's not much silver. In beta, there's mostly silver. There's not much copper. So that's at the high end. So this is still a simple system. It just has some additional phases and some additional interactions. So no liquid below that eutectic temperature. You can't have liquid below that eutectic temperature. It's not possible. Below that temperature, it's a combination of solid. It's all solid. It's just different ratios. So the composition at temperature E, the eutectic temperature, is the eutectic composition CE. So a eutectic reaction is liquid goes back and forth in equilibrium with alpha and beta based on these concentrations. And that's part of what we need to understand in order to understand how some of these tie lines and things will work on a slightly more complicated phase diagram. So for liquid, that means 71.9% silver. There's cooling and heating that happens across the 8 weight percent for alpha here. So this is our tie line. 8 weight percent silver in the alpha phase. In the beta phase, because we do have some beta at that temperature, 91.2 weight percent silver. So the beta is mostly silver. The alpha is mostly copper at that temperature. If we look at another material, so the lead tin eutectic system, this is something you can think of for the purposes of soldering. So lead tin solder was used for a very long time until we decided that lead needed to go away, and we wanted to change materials that would have ultimately a lower eutectic point, a lower melting temperature, and allow our electronics to degrade much faster, therefore rendering your cell phones mostly heaps of useless garbage within about a 5-year span. we used lead tin, and now we use some other material. So for a 40-60 ratio at 150, we take a look and see, okay, at 150 C, we have a 40% tin, 48% tin. We're in this alpha plus beta region, but what's the actual composition? What do we have? Our tie line here is about 11% in the alpha phase. So 11% tin in the alpha phase. Over here, we draw our tie line, and we have 99% in weight percent tin in our S phase. So we can look at the weight fractions to get the relative amount in each phase. So the weight fraction of alpha is S over RS. So the difference between 99 and 40 over 99 to 11 is about 67% alpha. So 67% is alpha, only 33% is beta, based on our calculation. So most of the material, based on a 40 weight percent tin at 150, at that specific temperature, this is the ratio of these two grains, the weight fraction. So it's roughly 2/3, 1/3, based on that material. So the same eutectic system, we now have a 40 weight percent tin alloy, but we've raised the temperature to 220. So we draw our line up from 40, because that's our starting composition. We then draw our tie line across to alpha and our tie line across to the liquid. So we're in the liquid alpha region. That's our composition. So alpha is 17% tin. Our liquid is 46% tin. From those, we can then calculate our weight fractions of 0.21 for alpha. So a little bit of alpha, 21%, and mostly liquid at 79%. So above the melting temperature, the majority of it in terms of mass is liquid. We would expect that if this is above that eutectoid melting temperature, as we're getting really, really close to melting. So that doesn't mean that the point is far, far away. That temperature point is far, far away from the liquid. It's below the completely liquid line, but it's pretty close. So we should expect the liquid to be a higher percentage, and that makes sense. All right, there's also a couple microstructural developments that can happen, and so here's an example of that, which becomes pretty critical. So for alloys where the concentration is below 2 weight percent tin, at room temperature, it's polycrystalline, and it has grains of alpha having a composition of C0. As it cools, there's some alpha that forms starting from a liquid. There's some alpha that forms, then it becomes completely alpha at all of the temperatures below that. Above that range, at about 18.3, there's a solubility limit. So let's take a look at that. So it's within this range, within the region that is bounded for including alpha, where we start to get beta included. We start at, in the alpha beta range, we start at a liquid. As we cool, we get mostly liquid with some alpha. As we continue to cool, in this region, we have only alpha in this phase envelope. Then we start to get some beta that grows in the alpha phase at a sufficiently low temperature. So below this transition, below this phase envelope, we get some beta particles growing in the alpha. So that should make some degree of sense that as we cool, we're going to change our composition a little bit. So let's look at one more example for an alloy where the concentration is equivalent to the eutectoid point. We start out a liquid. As we cool, we get combinations of alpha and beta below that temperature. And we get a rate of right at about 18.3 for our alpha and about 97.8% tin for our beta. So our alpha has almost no tin, our beta has almost all tin concentration, and there's going to be a zebra stripe kind of pattern, and that's actually what we see under the microscope. So that's exactly what that looks like and why it becomes as important as it does. So that gives us a pretty good range of what we're actually doing in these materials, and what that looks like on the whole. So there's a lot of parameters that are critically important there in these systems. So this is another closer look at what that lamellar structure looks like. So you have mostly tin, or mostly lead in the beta, mostly tin in the alpha, back and forth in that eutectic growth direction as those grains run into each other in all these different directions. This is what you're actually seeing under the microscope. So there's one more aspect of microstructural developments, and we'll pause this here because we're getting pretty long on this particular lesson. So we'll come back to this shortly.